Okay, we're continuing on with class 11. This is video 2. We're talking about Bernoulli, but now as it pertains to external work and external power, whether it's coming into or out of the system. So Bernoulli, as we write it, right? So a lot of times we will write it P1 plus 1/2 rho V1 squared plus GZ1 is going to be equal to P2 plus 1/2 rho V2 squared plus GZ2, right? This is a balance of the energy coming into a pipe or a control volume and the energy coming out of, right? And we said with Reynolds transport theorem is the mass flow in the m dot in and the m dot out. Of course, they have to equal each other because of continuity. But this is what transports that energy in and out of the system. But we can have outside influences that either take energy away or put energy into the system. One of the ways that we do this is we could have a pump or a fan that we include inside the control volume. And they could put add energy in and increase the energy at state 1 to state 2. Or we might actually take something out, like we could have a turbine. They could take and steal energy out, or maybe a driven fan. We can also have losses. Losses might be take place. So we can rewrite a new Bernoulli that has this, and our very favorite version is to do it with head. So we have shaft head and head losses, and it gets written out this way. And we reverse that for whatever reason. It gets written this way a lot of times. We take, and we're going to jump it. We're going to take the 2 and jump it over onto the left-hand side. We'll say that this is the outcome right here. And we divide everything by gamma, so we end up with a 2G over here, and then just a simple Z right here. And this is the head version, remember. So we can call it Bernoulli 2 is what I usually call it. So here's the end result, and here's the starting point. And then here is the additional part where we have we call a shaft head. This is not every book uses this, but this is HS. And then we also have head losses, right? And this right here is sort of our go-to equation for a lot of problems. So if you're looking in Sengel, which is disappeared, there you go. He's over here. This is very similar to equation 574 in your book. All right, so I'm going to try to tie this back into the stuff from the textbook. I say 574. Here you go. So this right here, you can see here's the turbine, right? You can see they actually flipped sides over right here. Okay, so I had 2 on the left-hand side, and I had 1 on the right-hand side. So you can see, well, here's the pump, and then here's the turbine. So they have both of them in here, and then they have head losses over there. So just be aware that's the same equation where I have now. I say the HS could be equal to HP for a pump, or it could be HT. Oh, excuse me. I meant to write this way. HS could be negative HT for a turbine, right? So because the turbine is taking head, as you could think of it, as head energy, it's taking it out of the system, so it's negative. And the loss is always taking the thing out of the system. So this is one of the go-to equations that we use. So if we want to say, well, what is this pump head? Pump head is taking the power. We can say I'll go shaft power divided by gamma volumetric flow rate, right? So this would be cubic feet per second, maybe. This is pounds per cubic foot, and then this becomes foot-pounds per second right here. And this just turns into feet. So this is like pump head, and similarly, we could have a turbine head. So this is also the shaft, gamma, and the V flow rate right here, right? It just depends on whether the shaft is putting power into the system or whether this is taking power out of the system. And we'll talk about the subscripts that this book, our book, likes to use here in a minute. So just, I'm going to rewrite this. Sometimes this is something we're going to put into here. Sometimes this is something we're going to find, right? Sometimes we're going to size how big of a pump we're going to need. We might solve for this, or sometimes we might want to find what the pressure is, so we might know this power that we got to put in, and we want to find what pressure or what velocity or something along those lines, right? So this is a very useful multi-purpose equation. So similarly, as I'd written in the previous video right here, we see that we have power is going to be this head times the specific weight times the volumetric flow rate. So pump head, pump power, pump head, gamma, volumetric flow rate, turbine power, turbine head, gamma, volumetric flow rate. And notably that this is a positive value for pump because it's adding stuff to the original. It's a negative here because it's taking stuff away from the original. Now, continuing on with another concept that we're going to use is very useful to us is the idea of efficiency. Particularly here we have mechanical efficiency, and we're also going to see that we have electrical efficiency. And what they have in common is we have input, or excuse me, I should say output versus input, but I like to say what you want over what you paid for. Paid for. There you go. What you want over what you paid for. And in the first law of thermodynamics, recall that you can't get something for nothing. Energy can't be created or destroyed, so you can't get something for nothing. And the second law of thermodynamics, you can't even break even. All right, so you can't even break even. You got to pay the piper every time you make some type of energy transfer from one form to another. So in this case, in mechanical efficiency, we have output versus input. So the input is what we pay for. The output is what we wanted. We wanted something, but we had to pay more for it than we actually had. So when it comes to pump efficiency, what that is that we have the mechanical energy input. So that's going to be the shaft work in, the shaft work rate, because that's power in. And what we're going to get out is the fluid energy. And what we often call this is, we'll say this is the work, the work the pump is doing as the shaft comes in. And here, this U that they're using that mean for, and that's going to be useful work, right? So we might be putting into our pump, right? So we have this little motor connected right here to a pump, and I'll make it look like a centrifugal pump. Here you go. Here's the output, and here's the input right there. Here's where the pipe is coming into the thing right here. And so we got fluid coming in and fluid coming out. But we have this shaft work shaft power that's putting right into there, right? So that's the input into it. But between these two things right here, this is the useful work power that's coming out. And that useful power is going to be less than the shaft work power that's coming in, because we have to pay a price for turning this shaft with a RPM and a torque and creating hydraulic power. That's the price we have to pay. That this power is going to be less than that power. Same thing true for a turbine instead, right? So if we have some type of turbine, we have some kind of energy coming in right across from here. The actual shaft power that we're going to get out from this turbine as it's being driven by this hydraulic power, it's going to be less. So this right here, this is the extracted. That's what they mean by this. I don't like these subscripts, but this is what the book is talking about. So this is the extracted power. So here is like the amount of actual stuff that we could get out of the shaft, out of the turbine right here. But here is how much extracted from the fluid. And so once again, we can't get out from the turbine as much as we put into the turbine. Some of it kind of goes away. Same thing true with when it comes to electrical power, right? So for a motor, we will put some electricity in. That's what we're going to pay for from the outlet. And this might be power is simplistically current times voltage, right? That's going to be electrical power. But the actual power that we're going to get out from the shaft, right? So we're going to have electrical power coming in through the wires, and what we actually get out is going to be less than what we put in. We just have to pay a penalty all the time. Same thing true if we're going to generate electricity instead. So if we have a generator attached to our turbine, we might get this shaft power that's been created by our turbine. Of course, we've extracted it from the fluid and turned it into shaft power. But now when we go to put it back into, connect it up to something else and be able to get our current times voltage, it's going to be less than what we had here. So we have these efficiencies and they get multiplied by each other. So in the scenario over here where we have pump, we will say, the efficiency of the pump motor is the efficiency of the pump times the efficiency of the motor. So we get a penalty for both of those right here. So if you're going to have the electricity that's coming in, it's going to be, sorry, I'll go the other way. If we want the pump, the useful pump work, that's going to be turned into hydraulic power. That stuff right there. We have a two-step thing. It's going to drop between the electrical to the shaft, right? So that the electricity is not going to produce as much power as you consumed. And then we're going to have a drop from the shaft in to the hydraulic power. So we're going to multiply the pump and the motor, those efficiency times the electrical energy that we went in. Electrical energy rate, right? So these are powers. Same thing true if we have some type of source of energy, and a lot of times maybe this might be a dam or something. So this is like, you could think of this as potential energy down here, and we're taking that and we're trying to extract it. So we extract some useful power out of this, the hydraulic power. Well, that's through the turbine, and there's a drop that takes place between the power that we've tried to extract and the shaft work that's come out. So the turbine has extracted some power, but now the shaft power is going to be less because of the inefficiency of the turbine. And then, of course, coming from this shaft, we go to the electricity. The generator has some inefficiency. So we pay another penalty there. So the actual stuff that we want is going to be the electrical, but we have to take two penalties. One is going to be for the turbine and one for the generator, and multiplied by the extracted turbine work. And actually, if I were to do this, I would call this hydraulic power, right? Because we want to generate hydraulic power here, and we want to take out hydraulic power there. So I'm at my end of my spiel talking about the big ideas. Let's go do some examples in the next video.